Over things. Fabian, have you caught up?
Yes.
Settled everything?
Yes.
Okay, so we postponed the homework, right? Let's see here. Right? What do you guys prefer? Maybe I asked before, do you guys prefer in-class exam or sometime in the evening with extra time?
I prefer in class.
In class. Okay.
Okay, maybe in class. That is fine.
Okay, so it seems like. Okay. Okay, we were doing vector field calculus, like we differentiated between vectors and vector fields, and then said that the moment you have vector field, we can talk about differentiations, and that's what we want to do today. But before that, we should deal with how to work with vectors itself in a convenient manner. So we introduced what is called index notation, and we did not completely finish it last time. So let's do that. So we introduced, so let's call this index notation. So, that. I think it's also called Einstein summation notation. Maybe that's the better way. So the idea is that if you have a vector dot product, then this is easily written as we know that it is a1 b1 plus a2 b2 plus a3 b3 in a particular coordinate basis, with the understanding that there is a choice of basis vectors. And this is also conveniently written as ai times bi. That should be a summation over I, but that's the whole notation, that whenever an index is repeated, it's understood that there is a summation in it. This is also in terms of a second rank tensor. It's also written as ij. So now there is summation over 2 index. But this is, and it's good to, or there are various ways of looking at it. Right? Algebraically, this is just a1 b1 plus a2 b2. Sometimes the algebra has a little, it gives you more insight if you see this as a matrix multiplication. There is a vector A, then there is a matrix 1, and there is another vector or a column matrix if you want. So this is also the same as a1, a2, a3. This is 1, 0, 0, 0, 1, and then there is b1, b2, b3. These kinds of products are called scalar products. And this is the simplest scalar product, where this is an identity matrix. You can think of a generalized scalar product where this is a fixed matrix, right? So that we do use that in physics. The simplest one is when 3 plus 1 space-time dimension comes in Einstein special relativity, the time one gets a minus 1. So the scalar product becomes minus 1. So these things we will come across later on. Currently, this is good to recognize that this is a dot product, and this is also written in terms of Kronecker. So we introduce the idea of Kronecker delta symbol. And the symbol. Equal to 1 if I is equal to j, and is equal to 0 if I is not equal to j. Efficient. So that's dot product. We then started talking about cross product. Now this is a vector, so we would like to talk about the index third component of a vector product, or a second component of a vector product. So since it's a vector, so we say ith component, and that's, we said, is written in terms of a third rank tensor, epsilon ijk times aj. Again, there is a summation over j, there is a summation over k because it's repeated. This is a vector on the left hand side. I is called a free index. J and k are dummy indices. So that means to say I can replace j and k with mn or pq, doesn't matter, but I has to be balanced. If there is left hand side there is an I, right also has an I. So that's like saying that if left hand side is a vector, right hand side has to be a vector. Vector cannot be equal to a scalar. This is in terms of a third rank tensor now. So this is second rank in the sense there are two indices. Here there is three indices, and this we call Levi's. I always
C.
C5. And this is equal to 1 if ijk is cyclic. So let me write that in this way. So if ij and k come in 1, 2, 3 order, that's cyclic. It is equal to -1. Choose this. It is equal to -1 if it is anticyclic. So that's ijk this time. And this is equal to 0 otherwise. And it's good to recognize there are how many components in there. There are actually 3 into 3 into 3, 27 components. And how many of them are 1? How many of them are -1? How many of them are 0? So here is a quiz, or we typically have quizzes, right? Right, all the 27 components done, right? Just as an exercise. It's trivial, but I think once in life, I think it's good to, and if possible, organize them in your own way. But yeah, I mean, homework is, or quiz is just to get all the 27 components. The quiz is list all 27 components and recognize how many of them are 1, how many of them are -1, and how many are 0. If possible, organize them properly. Okay, so that's where we were, and then next idea was to be able to use this in more complex vector identities. So this is vector product, scalar product, but this can be combined very easily. And for that purpose, we introduced an identity. So change this a little. So introduce the identity that if you have two, you said ijk and lmn. Now, how do you see this? That instead of proving it, it's basically you try to verify it. But the idea is that the Levi-Civita symbol is antisymmetric in the swap of any two indices. I can replace I and j, you lose a sign. J and k, you lose a sign. And the same thing in these three. And if you recall in matrices, determinant also has exactly the same property. So as far as numerically you can match it, there must be a one-to-one correspondence. And you can, in that, using that idea, you can build this. This is a determinant now involving, write this down and then L, M, right, that's a determinant. It should be, if you think of it as, remember that this can also be thought of as matrices, right? So these are elements of a matrix where they're matrices in the sense that each one can take on certain values. These are components of a matrix. That's the way to look at it. So using this, but we can have a lot of identities, and the best is to contract, right? So there's this is a sixth rank tensor, no dummy variables at all. It is only free indices, 6 free indices, and 0 dummy variables. But the moment I start contracting, so let's start with the idea that yes, please. Yeah. Okay, so let me just so that I can match I and J and M and N, I'll move it to the left and move K to the right. So this is K, I, J, L, M, N. Sorry, I won't write K, right? K, M, N. That's what we did last time. This is the same as epsilon I, J, K, epsilon K, M, N. Why? Because if I move K and J, once I lose a sign, I again do it, I lose 2 signs, right? So in that sense, this is exactly the same as this, as far as I put L is equal to K everywhere. So I put that in and try to get an identity. And so that's delta I L multiplied by this 2 by 2 matrix. So, but L is K, so that's delta I K times delta JM, delta KM minus delta KM, delta J. Is that clear how I wrote this? I multiplied this like as if you do the norm of determinant multiplication. Next one is this only place where L shows up is here, right? So let me start this. So this is minus delta J K. So I'm starting with this, this, and this. So this is equal to delta I M delta K minus delta K M. Last time I started with this because it doesn't matter really. I just did it this way so that I remember to write L. Last time I forgot to replace L with K. So it's plus delta KK times delta IM delta JN minus delta JN. Okay. Any questions at this stage? We already discussed this. What is delta KK? This, what is this equal to?
3.
Okay. Is it 1,
3.
3, right? So we said this is a repeated index. So there's a summation over K. So that's equal to 3. And let's do one more thing here. So that is a, let's see if there's any products, immediate products. So as this, when you multiply this delta IK, delta KN, so this is delta IK times delta KN. There is this combination here. What is that equal to? Delta IN, that's very good. So there's a summation. This is like 2 identity matrices multiplying together, you can almost visually see that. So that will be equal to delta IN. Very good. So there is summation here. If you have any confusion on why that is delta IN, explicitly do this. There will be 9 components in here. On the right side, there are 9 components. On the left side, there will be 9 components. Explicitly evaluate each one of them. And you'll notice that whenever there is a chronicle delta symbol, it's basically what it does is that in the next matrix, whatever it is, it will get rid of the K and replace K with I. Whether it is a normal matrix or a delta, it works the same. So you can work at the left or to the right. So using these properties, so let's try to write this down. So this is delta JM, and I have replaced delta K gets replaced with I, delta IN. Right, that's the first one. The second one, again, K gets replaced with I here, right? K gets replaced with I here. Same thing is happening. So this is minus delta IM, delta GM. Let me know if there's any confusion. And now here, again, K I'm replacing with J here. So this is minus delta IM, delta JM. And then this is plus of K gets replaced with J, delta GM. And this one is just 3, right? So it's plus 3 delta M GM minus 3 delta JM delta IN. If you notice, these are all the same structure. There is a, let's start with I and an M, right? So there is 3 of them, delta IMJN, 3 of them here. This is the same, delta IMJN, there's a minus 1. So I can underline them. This, and this are the same kind. Right. So there's a factor of 3, minus 1, minus 1, so that's plus 1. So this is delta IM, delta JN, and minus of the rest of them is another same kind. But this time it is minus 3 plus 1 plus 1. So it's minus of delta JN, delta I, sorry, delta M, delta JN, delta IN. So dear, this is a very useful identity. You will see it enough that often you get to memorize this itself. Notice what we have got is that delta Kij, or delta Kij times delta Mn is equal to, notice how it works. K is summed, so it's gone. It is a dummy variable. I goes with J. No, I goes with M. The first one goes with M, and the second one goes with the second one. And then you swap. The only other possibility is that I goes with N, and then J goes with M. I goes with M, J goes with. This is basically what is inbuilt in when you're doing a VAC rule. So let's look at that. Any questions at this stage? Right, that's an identity we have seen. So now let's go and see what is A cross B cross C. That's a vector, and let's say I summed, so let's
epsilon ij
ij and
aj because b a dot b minus c a dot b.
yeah, so what's the index I want to use? So give me a second. Sorry. Let me write it down. Okay, so if this was the ith component, but I'll change this in a minute, probably. So this will be epsilon I
gk
g k
aj
okay. Again epsilon yeah k m n m c n k k, yeah, that's the same structure. Good. Okay. What's the on the right side? Is this how many free indices on the right side? One.
one
There's one free index. How many dummy indices?
altogether
Four dummy indices, right? Like I is J is summed over, K is summed over, M is summed over, N is summed over. So four dummy indices, one free index, so it's a vector. Once you write it in this form, understanding is that for every free index, these are numbers, you can move things around. Like here, you cannot move things around, right? A cross B cross C is not the same as B cross C cross A. The order matters, parenthesis matters. Here, it doesn't matter. So you immediately say this is delta. I again move the K 2 times just so that I can match with that. So it's K I J, K M N times A J M C N. Use the identity we just now have on top. So that's equal to delta I M delta J M minus delta I N delta J M minus A J M C N. Notice now there is I have a delta chronicle delta. I am going with DM. So what will delta I M DM be equal to? What is that? Repeat.
that is bi
BI, right? So what you do is this survives only when I is equal to M. So basically the idea is replace M and replace M with the I. Wherever M comes, it's only I. Whenever M is equal to M, that is the only time it contributes, and the free index is I. So appreciate this practice. The basic idea you use, little practice. So this becomes I now, right? So M gets replaced with I, J gets replaced with N. That's what it does practically. So this is AJ, DI, and CN gets replaced with J. Is that clear? And this is AJ, DJ, CI. Is that clear how I did that? Any questions on that? Like after a few times you work on this, this should become second nature. Like even you should be very fluent. That's a basic step that you will need to do. Any questions on that? If you have any concerns on that, you should ask. Yes.
Could you, why did you choose I and J instead of M and N? Does it matter?
Why did you use what? Oh, yeah, it doesn't matter because J is dummy, right?
Right.
It doesn't matter. So
Right.
maybe what you're saying is that, oh, why did I replace when I did, for example, Dale chair? Your concern was, what was the question?
Yeah, so like when the JN and the JM, why wasn't it the other way around? It's just why I was curious. Like not AM
Because it is summed over m.
or AN, BM, CN.
I think what you're trying to say, give me a second, is, yeah, I know what you're saying.
Like you made NJ.
Yes,
So
why
we
not,
make
why not
J-
make JN?
Right.
Same, it's dummy,
It's the
it
same
doesn't
thing.
matter.
Right, okay, yeah.
So I think your point is that this is also equal to, I could have started from here and said, yeah, J is summed, so replace J with N. So this is the same as AN. So M is replaced with I, that is unique. And this is CN. Is that clear? Right. If you replace J with N, right? J is replaced with N, then you get this. And N remains. So N remains. And you can do the same thing here also. Here I replaced N with J. What did I do? No, N with I. So I replaced M with J, but I could have done the other way. I could have replaced J with M. Right? So this is also AM, BM, C. Good point. Right? Because I mean, one would have done it this way, someone else would have done it. If you replace J with M, you get J with N, you get this. If you replace N with J, you get this. Either way, it's okay because remember, dummy indices can be called anything. I can call this A, B, C, D, anything, right? As far as it's remitted. So that's fine. Okay. So now, so since this is a math methods course, if you're doing, for example, electromagnetism, usually these are electric fields, right? Electric field crossed with magnetic field crossed with another vector. And they're all classical objects. By classical objects, I mean the elements of this matrices or the vectors are numbers. The electric field at any point is a number, right? But it is possible that A is not a number. And if it's not a number, what could it be? Vector, yeah, but some vector also, its components are number, right? Can you think of something? Yeah, it could be matrices, like A, B, and C could be matrices, or in general, the word is operators, right? So in quantum mechanics, you come across not just quantum mechanics, there are two things. One is a gradient operator, right? For example, gradient, a vector acting on E is not the same as E times gradient operator, right? Order matters. So it is possible that you will come across things that are not respecting the order. Like A times B is not the same as B times A, like matrices A times B is not the same as B times A. Then you cannot move this. See, now I would like to move this on the other side. So let me write this down as if, right? If A, B, C are numbers, so AI, BI, and CI are numbers. And when I write AI, BI, CI, I mean ith component of A, B, ith component of B, I can use any index, right? If you can move things around, then you can write this as BI, correct? Times A and CN minus, if you want, I'm moving AB now, right? So this is written out. Times CI. And then you see that, oh, this is A dotted with C, right? So this is a vector B, A dotted with C, minus A dotted with B times C. Is that clear? Notice the step that I had to move this B out of this. That need not always be true. And we'll come across right now, we will do an operation where we won't be able to move this. If we cannot move this, then we have to be careful, and then we will see how we can go around. If it is not allowed to move, then you whatever is the subtraction you have to add, right? So that's what you do. Is that clear? So this identity that A cross B cross C requires the fact that you can move B, like A commutes with B, or the components of A commutes with B. That means to say 2 times 3 is the same as 3 times 2. The vector components here are usually numbers, like in electromagnetism, electric field. These are numbers. Classical mechanics, these are numbers, but in quantum mechanics, they are not. In fact, in electrodynamics itself, if you come across this gradient operator, it's not. And that's what we will do just now. That if you're working with gradient operators, then this has to be generalized, or not generalized. Everything goes well until here. At this stage, you have to do something else. Okay, is that clear? Okay, but before I get into that, let me play with some indices here, at least one example. Any question at this stage? Okay. One more comment I will make. This can be thought of as a distribution, right? You have, whenever you have a parenthesis, you multiply A times B, and then you multiply A times, right? So this is a distribution of vector products. When you have 2 vector products, this is how they distribute. Like in differentiation, if you have differentiation of A times B, you first differentiate A, then you differentiate B. There are 2 terms. So this is kind of a distribution property of the vector product. Very soon we are going to do differentiation, and these things will combine together. So with those comments there, let me go back a little, and let's we have so we have epsilon k I j epsilon k m n to be equal to delta I m delta j n minus, relatively easy to remember, right? Like 1 goes with 1, and then you just start. I n. And remember, this should have an antisymmetry property. If I replace I and j, it should change sign. If I replace m and n, it should change sign, which you should be able to check on the right-hand side. We started with a 6th rank tensor. We contracted. Contracted means we set k is equal to L, and we got this. Now this is how many free indices? 4 and 1 dummy variable. So that means it's a 4th rank tensor. I can again do the same idea, set one equal to the other, which is called contraction, and I'll get a 2nd rank tensor. So let me set I is equal to m, right? So this is delta k I j and k I n. How many free indices? 2 free indices and 2 dummy variables. So this will be a 2nd rank tensor. We just have to set m is equal to I in this. So this is delta I delta j n minus delta. I'm setting m is equal to I, right? So this is I n, and this is j I. And that's equal to, what is delta I? 3. Okay, so it's 3 delta j n. And what is this? Now that is summation over I. So I have to replace I with n. delta Jn, and that's equal to 2 times delta Jn. Maybe. Yeah, where do you come across this? I think it's a quiz here. So in electrodynamics, you have this identity del is equal to, or magnetic field is given in terms of a vector potential as a curl of the vector potential. If you're not familiar with this, you'll come across this. Currently, this is just a vector identity if you want. But now, sure, if you have start from A, so start from the second line, substitute on the right hand side, and show that that's equal to B. Okay, so maybe I should write that down. So that's 1, equation 2, substitute 2 in the right hand side of 1 and verify 1. By verify, I mean if you put this on the right hand side, you should get a B. And be very careful, don't try to get the answer. It will turn out that if you try to get the answer, you will miss on something. It's not straightforward to substitute this and get. Use your vector identities, be careful, and tend not to make a jump. The whole point is that when you have the first step and the last step in front of you, it is very easy to say that, oh, this is equal to this. So that's it's very prone to mistakes here. So just be careful. And I think there is an essence, or typically, nice. Yes, Krishna.
Are there parentheses around that B cross R? Or is it just one half B cross R?
It is B cross R here, but when I substitute this in that, that will become a parenthesis. Is that what I mean?
Yeah, I just didn't know. Okay.
Yeah, like here it doesn't matter because A is equal to this. The moment I put it in there, then it's important that I put a parenthesis in there. Yeah. Without at this stage, it's okay. Yeah, good. Okay. We can go further, right? So this was a 6th rank tensor. This is a, no, we started with the 6th rank tensor. This is a 4th rank tensor. This is a 2nd rank tensor. Do one more, right? So this is Kij. And Kij again, right? I replace everything and I'll leave that to you to find out, right? Will this be a vector which this is what's the rank of this tensor? 0 rank tensor, which is a scalar. That means this will be a number. This will have just one component. This will just be a number. So it's good to know what is that number equal to. So I leave that to you. You can almost immediately read it out what that is going to be equal to. So you just start to replace n with the j. The moment you replace n with the j, that's delta jj. Delta jj is 3. So 3 times 2. So that's 6. So it's okay with all that. So now we know how to basically do do double cross product, let's say. Right? So one counterintuitive thing we learned is that A cross B cross C, which we knew all the time, but now we want to exploit this further. This is equal to, let me write this properly. So let me go back and not do this step here, right? So this is, let's say AJ to ICJ, right? This is ith compound. If there's any confusion, maybe sometimes I and J are treated similarly in your head. So let's say this is M. I is the free index. And this is like back, right? A and C are dotted, dot product, and B is minus cab. So this is AM, M, C, I. Okay. Now, we also remember that if you have the gradient, or let's just take differentiation, right? So if you have simple differentiation, d by dx of a function f of x times a function g of x, this also distributes. Right? So we have the derivative of f with respect to x times g minus of f times derivative of g with respect to x. Think of this as a distributive property. In fact, it is more than that. There is a nice way of looking at cross product as a calculus of non-commuting objects. But at this point, I'm just interested in the distributive property. This distributes, this also distributes. This is just one dimensional derivative. If I have gradient acting on, let's say, two quantities, instead of f, I write b, right? And this could be a vector. So as of now, I simply write c. When I don't write a vector, it means it's a scalar, right? B and C are scalar functions. Here, B and C are vector functions, like they're different entities altogether. The moment you say one is a scalar, one is a vector, they're different quantities, right? But I'm using the same symbol because I want to immediately go back to the vector on it. Maybe I'll write B and C, right? Small c, B and small c. Small b, small c, right? What will this be equal to? Again, the same distribution, right? This can hit on this, or this can hit on this. Idea is that these are all fields, right? These are position dependent quantities. So idea is this is gradient acting on B and C minus the gradient acting on C and multiplied with B. Now again, if C is numbers, this is the same as C can move around. C can, after it has acted, I can move C around if C is a number. If these are matrices or if these are operators, I cannot do that. So this is the correct positioning of that. This acts on B, this acts on C, and that's the way you would position them if you're not allowed to move things around, or if it costs you something else to move things around. Okay, so that's now this is interesting because this is now a vector, right? So this could come in a cross product. So we want to talk about what happens to cross product when there is a gradient acting on it. So gradient will have this property, but if B and C are vectors, they will also have this property. So there is a distribution because it's a cross product, double cross product. There is a distribution because it's a gradient. Together, they will go 4 times, 2 and 2. Okay, so let's see how that comes about. So let's talk about a vector identity involving 3 vectors in which one is a gradient operator. And again, the idea is that B and C are fields, so these are position dependent. Right? I'm not writing it. This is not simply a vector. This is a vector field. B and C are vector fields. Is that clear? Any questions what we are addressing here? First thing is, as far as we make sure that everything is acting on that. So this should be okay. So let's say this is the ith component. So first I'm going to take use the vector identity here. And now this is M, right? So this is M bi CM. I'm only expanding vectors. I'm not worrying about gradient operators still. So which means that this has to act. So just to clarify that this has to act, I use parentheses. I say that this is supposed to act on both. Right? This parenthesis here in my head means that this is to act on this has to act on this, this has to distribute. Minus of the same thing, this is delta M dm ci. Like if it was simple vectors, I don't have to do anything more. There is no need for parentheses. But here again, I keep in my head that gradient has to act on this, so this has to distribute on that. Okay. It's still a vector in the sense this is ith component here, but now this will act on this will act on that. Now I use this property and make it act. So there'll be 4 of them, all right? So this is M I. So now I have acted on that, so I have to stop this. Right? So I use parentheses to clarify that. CM plus BI minus
plus or minus,
which plus or minus?
second term.
Oh, here.
Yes.
What is this minus? For that matter, why is this minus? It should be plus, right? Yeah. So that's a mistake. Okay. So like this is differentiation, right? Right? Yeah, my bad. Very bad on my part. Sorry about that confusion. So this is plus. Okay? This is plus. This is plus. There should be no confusion. Okay, sorry about that. Okay. So I think I was just carried away with the pattern that not acceptable. Yeah. Okay. That's plus. This is minus, but this is plus. And yeah, now I was writing it. Okay. And this is delta M and Ci. Is that clear? Sorry for that. Okay. If now again, if B and C are classical, C are numbers, or if they commute, right? If they commute or they're numbers, then I can move things around, right? C can come on the front, C can come on the back, that's okay, but not in quantum mechanics again. In matrices, it cannot happen. So if that is allowed, then you can write CM M BI. This I will leave it as it is. Plus, and I don't use parentheses at this stage. because it is clear that if on the right hand side there is only one function, this cannot act. Typically, the derivatives don't act on the left hand side, right? So I dropped the parenthesis just because there is no need to clarify. This again, no need for parenthesis. It's clear without the parenthesis also. There is no ambiguity there. This one, there is an ambiguity because I want to keep it as it is. So this is delta M. I'll keep the parenthesis there. And here, I don't need the parenthesis. C M delta M C I. Right now, there are 4 terms in this expansion. But notice it came pretty much same as earlier, but this combination of derivative distribution and the vector product distribution. Christian?
Yeah. Why was I missed it? Why was the parentheses kept on the?
Because if I don't write the parenthesis, it's not clear whether this differentiation acts on C or not. Right? So, for example, if I write derivative d by dx of f times g, and if I write d by dx of f times g, here it is some notation. I'm not sure d by dx acts on f or both f and g or only on g. This is typically there are some notations. Most often, or many textbooks assume that if I don't put a parenthesis, derivative acts on everything on the right. Right? That is one notation among some set of people, but that's not obvious. Like right away, unless the book says that in the beginning that this is a notation we use, that's not obvious. Right? But often many people in theoretical physics, especially, they like because they want to avoid using parentheses. After a while, there are so many things in there is a matrix there. If that or parenthesis has only once it can capture that, right? So you try to build in the notations sometimes. But I'm not using those notations. So in the absence of those notations, it's not very obvious whether this is acting on C or B alone. So it's just clarifying. In other places, it's clear. There is no ambiguity there.
Thank you.
Okay, so this is a dot product, right? Whenever an index gets together. So now let's go back to writing this as a vectors. So this is C dotted with del gradient. And again, gradient has to act on something. So if it is not acting on something, the idea is that this is an operator. So this is B, which is a free index in this. This is B is the free index. This is a dot product, right? This is typically when you do calculus or vector calculus, this is the derivative in the direction of C. Like if you have a plane, the gradient can act in any direction. Right? The gradient operator is very general. At a certain point, you can have a gradient operator in any. So that's what the gradient operator is. If you're on a mountain, it tells you what's the gradient in each direction. Right? That's the idea of a gradient operator. This has a special nature. This is the gradient in the direction of C. Right? So for example, if you have a if F gives you the profile of a mountain, correct? And now you're sitting on Mount Everest. In each direction, its slope is different. Right? If I go in this direction, it's very steep. If I go in that direction, it might be less steep, and so on. You might be interested in finding what's the gradient in the direction of east, right? So then you would say gradient in the direction of something. So if it is east, let's say this is I hat, then you would say this is I hat. But in general, it could be any vector. Right? What's the gradient in the north is 30 degrees north of east? Then you would put that particular vector and put it in here. It could be a whole vector field itself. Right? Given C, what's the direction of the gradient? Gradient of this B in that direction. This is more than a gradient in the sense gradient operator acts on a scalar, right? this is acting on a vector. So maybe I should say, what is gradient of a vector? Let's say A. Notice I did not put an operation there, right? If there is a dot there, if it is a scalar product out there, then that's a divergence. Very good. If I put a curl there, that's a curl. This is two vectors coming together. This is a tensor. Right? There is an I there is a J there, right? That's the way you would interpret it in index notation. So this has 9 components. This is often said an outer product. Okay. So it doesn't come often, but in electrodynamics, it's called a dyadic. Right? Whenever you see the flux of momentum in electrodynamics, which you will see if you're going to do E&M here, the second semester or the third semester, it's a flux. So when you say momentum, also light is going in that direction. So you can ask, while it is going in that direction, what's the pressure it is exerting on the right side? So that's called the flux of the momentum, and that will have a structure like this. So it's like stress. Yeah, for example, sometimes you have a material, right? You have a cuboid material. Let's say its material properties are anisotropic. Often, if you push on this direction, you get a pressure in that direction, or you get a momentum in that direction. Right? You can also ask, if I'm pushing an object in the I direction, what is the momentum in the J direction? Not very trivial, right? You would say that it's 0. But sometimes there are motion possible in that direction. Then you say, what's the flux of the momentum in the J direction because of an action in the I direction? So that involves these kind of quantities. These are tensor objects or stress tensor. If you do engineering, this will be called stress strain analysis, or something like stress and strain. But here, we are just keeping it as general. We don't know what CMP is. It comes up in this form. Here, the next term is B is the free vector, and this is del C. And remember that I replaced B and C here, right? And that means to say that this cannot be done in quantum mechanics. If you have to do this in quantum mechanics, then you have to write this on the right side. So it's not easy to write it, but that's what it is. Okay. Minus of, you said divergence. This is divergence of B. This is divergence of C, and so on. Okay. So there are two divergences coming in and two, in a sense, gradient, or if you want flux in the direction of C, or let's say gradient in the direction of C. That's the way to put it. If acting on each of the components. That's okay. So a vector identity has 4 pieces in it if you have a gradient operator on it. In your homework, you have to do this for other operations, right? But the basic idea is just this, that this, you have to accommodate this and the vector identity. Any questions here? Yes.
So the BI and CI are numbers, or BM and CM also numbers?
Yes, BM and CM. Any of the components are
Okay.
numbered. If it is not, okay, so that raises a question, what if it is not, right? So let's try to see what happens. So I can motivate that. You don't do anything, it's just that you try to do the best you can. But I give you an idea of how it is, how you proceed on that. So this we did not move, this we did not move. It's just this, right? So So if there is no things don't and commute, or they do not commute. So this is equal CM no, sorry. Other. That's the same. Let's say that delta delta of m help here. Yeah, delta of m p of I. This is an object, right? Whatever that object is, it's there. So if this as a whole, is this a scalar, tensor, or a vector? Is this a scalar, vector, or tensor? Tensor, right? Free index, there are two free index, so it's a tensor of prime 2. So that object, let's say what this is with respect to Cm. So this comma means, now there's a bracketed quantity I've introduced. If you're seeing quantum mechanics, what this means is that this notation is commutation relation. A comma B means A times B minus B times A. So when I did this there, I moved this. So this is equal to delta M I times Cm minus of Cm times delta M bi. Right? That's just definition. But in quantum mechanics, often you give relations to this. For example, if you recall Heisenberg uncertainty relation, so that's Heisenberg uncertainty relation is what?
Position and momentum.
Position and momentum. I mean letters
X and P.
X and
P.
P. Right? That's equal.
X minus PX.
Yeah, X3 minus Px. What is that equal to? I H bar. That's good, but this is one dimension. Right. So now I can ask. Now I have a vector. Right. So this is a vector. Position is typically in 3 dimensions. So that's a vector, and then this is P. That's also a vector. What is that equal to? That's a generalization, and you will immediately ask, oh, what do I mean by that? There are lots of terms here, right? So there's x comma px, right? What is that equal to? I can write what is x comma py. What is that comma equal to? Like position in the x direction and momentum in the y direction. How are they related? Right? What about x comma pz? And then I can write y comma px, and so on. So there are 9 pieces in there. So when you say, the moment you go into 3 dimensions, there are 9 components to this, and I should know what is that equal to. What is that equal to? IH bar, surely IH bar will be there for dimensional reasons. But what is that equal to? Again?
Yeah, not sure.
Yeah, I'm sure. You think? So, this is symbolic. Let me say, what is x comma px? I was trying to write that down. Y comma px. Z comma px. X comma py. Y comma py. C comma py. And then we have x comma pz. How many things do you know? X comma px, you know, is IH bar, right? That you know,
3 I,
right? Three?
so 3 IH1.
Three IH bars, right? So this is IH bar 2, this is also IH bar, right? That's because one each dimension. So then the only question comes is that if you have position in one direction and momentum in the other direction, that's not very obvious, but as Heisenberg's uncertainty relation is a law, right? It is a postulate sort of, and it is zero. So the position in one direction and the momentum in the other direction does not cause any error in the other one. So this is zero, that's equal to zero, that's equal to zero, that's equal to zero, that's equal to zero. If that is the case, now that you have given you all this information, what is this on the right hand side?
3 IH.
3 IH bar. What is on the left hand side? Is this a scalar tensor? What is this equal to? Is this a scalar? Is this a vector? Is this a tensor?
The vector.
Let's write that explicitly. So I'm asking this. So this is x times p, right? Minus of p times x. That's what it is. Right? Is this a scalar? Two vectors coming together. Is there a dot product in there? I didn't write that. Is there a cross product? I didn't write that. So the two vectors, this is a tensor, right? It's called, often in many textbooks, they will write this like this. If you put a cross there, it's called an outer product. 9 components, right? 1, 2, 3, 4, 5, 6, 9 components. What has 9 components? Tensor, right? Tensor of second rank tensor. So this is a second rank tensor. So there has to be a tensor there. Second rank, if left hand side is a tensor, right hand side has to be a tensor. So what is that? Which tensor has this property? Identity matrix, right? So you would write this as, so now this is a new symbol. I would like to write this as IJ, but often you will write this like this. It's an identity matrix, or if you wanted to write it in index notation, the best is index. It's when you're learning, index notation is the most unambiguous relation. So you would write this as xi, comma, pj. This can take 3 components, this can take 3 components, and that's equal to IH bar delta ij. Okay, so that should be very clear. But often this is written in that form in dyadic notation. This is called a dyadic notation. Okay, but this is what we are doing. So let's concentrate on this. Any questions on that? Okay, but you'll see that as quantum mechanics, we won't work on it too much. But I was saying that this is all to motivate the fact that this is a commutation relation. In quantum mechanics, usually this is equal to something. So I can set this equal to something. Let's say this is equal to a new quantity, D, right? Like for example, IH bar, that was a law, right? So in quantum, for some reason, you know that this is equal to this. What is, how many indices underneath this? What is this equal to? Is this a scalar, vector, tensor?
Tensor.
Tensor. So what are the indices?
Right.
I and yes, the tensor. So tensor must be, otherwise you would have said vector, right? Is this a vector or a tensor or a scalar?
Tensor with IM.
I am. Is that correct? On the left hand side, how many free indices? How many, like, take this piece, one free index, right? One dummy index. So that's a vector. Correct? If this is a vector, this is a vector, correct? This must be a vector. This will have only one component. That's why I was misguiding you guys. So, all right. That's kind of tricky, sorry. Didn't mean to. But is that clear?
Yeah.
So this is a vector because this is a product, right? Even though I am writing it as in brackets, this is each piece of this is a product, right? So n comes twice, so it's actually a vector. And let's say that this is given. So this is given. So this is an additional information, only happens in quantum mechanics. If you're doing electrodynamics, this will be 0, right? Number commutes with number, so at each point in space, so this will be 0. But in quantum mechanics, it's possible that that might be the case. Oh, I forgot to move the board back. So if that is the case, what can you do about this? So this is equal to, so this is how you will work in quantum mechanics. If you have to deal with this, but now you would like to move C on the other side so that I can write a dot product. I want to move C on the other side so that I can write it as a dot product. So I want this. So I have this down here. I want this equal to this. So this is equal to, or let me just write that. So what is dm delta m bi? What is delta I? Delta m bicm is this. This minus this is equal to di. So that's equal to di plus cm delta m bi. Correct? So if you were doing del cross b cross c, let me say this is quantum mechanics. In quantum mechanics, correct, is equal to the same identity in, let's say, classical mechanics or electrodynamics, let's say classical mechanics. Is that clear? Which will involve this term, but it will give me this extra di. I will replace that di in there, so this will be plus vector d. Is that clear what I did just now? Awesome. No. Okay, so let me go back and verify this. So what I meant is that this that I wrote, this is the classical mechanics. Okay, this is the plus CM. If I write, that's this. Right? Now I'm doing quantum mechanics, which means this is D. So let me go back and L cross D cross C, quantum mechanics with the ith component there. I start from here, but this one I showed is this. So this is CM, M, DI, plus DI. That's this replacement. Is that very clear? That should be clear. And then I write the rest, right? Plus DI, delta M, CM, minus delta M, DM, CI, and minus of DM, delta M, CI. What's the difference between this and this.
The D.
The D is the only difference, correct? So, but I call this whole thing Cn, correct? In classical mechanics, so I say that, okay, this is equal to D, which is a vector, so I write a vector there, I, plus tau cross D cross C times classical mechanics. Is that clear what I mean? This always happens. Whenever you start from classical mechanics and go to quantum mechanics, you get a new term. That means that's new physics. If you were doing an experiment, if you can check this, that's usually very, very good, because now you got a good new thing that is not there in classical mechanics, but it's there in quantum mechanics. Okay, and this is very common. Typically, this will come with an IH bar, because a Heisenberg uncertainty relation has this IH bar, right? So anything that has an H bar, that's a quantum mechanical effect, and it's usually very beautiful. And there are tons of that in this century. In the last 120, 130 years, we have seen tons of those kind of effects, where it's not there in classical mechanics. If you do Newtonian physics, you don't get it, but you do quantum mechanics, you get it. And mainly because of this algebra, right? That commutation relation has this extra piece in there, and you do this, oh, there's a new piece. So experimentally, you go ahead and do this. Oh, yes, we do see this experiment, which means that our old physics was not complete. Is that clear?
Yeah.
Let
Let me stop there, and unless you guys have questions, yes.
Yeah, so the D that was given with a commutator of between those two things, you could give a new one, right?
I can do that. This is, since it's a math methods course, I'm not talking about a specific law here.
Right.
It could be anything,
Okay.
but typically this is dictated by, in quantum mechanics, everything is dictated by one new law, that's Heisenberg's uncertainty relation, X comma P is equal to IH bar. So everything starts from that.
I see.
So everything comes from that specific thing. But if you're in an advanced course, you will use something else. For example, the classic thing you do is, like for example, we do the hydrogen atom problem, right? Planetary motion. You study, what is this? You study Newton's law of gravitation. The first thing you do is, oh, I have a differentiation of momentum is equal to g m1 m2 over r square. Solve this, you will get the Kepler orbits. That takes a good amount of work, but you will get the Kepler orbits. Now you do the same thing with this fact in, position and momentum do not commute. You do the same thing, you will get hydrogen atom as the solution. It's exactly the same. If you put h bar equal to 0, you will get planetary motion. But if h bar is not 0, you get some extra terms, and which has huge meaning in that. Right? That's one piece usually, an extra piece in any equation that you write, but its meaning changes dramatically. And that's how quantum mechanics was invented, right? It was invented in hydrogen atom. So it's good to see it in this context if you want. So it's one way of motivating it. Okay. Other questions? Comments? Okay. You guys have a class now, I guess, right?
Thank you.
Okay. Good.